Large Hadron Collider. The world's biggest atom smasher turned on, and a small court case asked if it might make a black hole and end everything. You remember the image? A machine so powerful it could tear a hole in reality. Headlines fed that fear. People called it an experiment that could delete us all. The first real scare came not from theory, but from a messy startup. In 2008, a massive helium leak and an electrical fault forced a shutdown for more than 1 year. That failure made the machine feel fragile. It made abstract physics into a headline that people could be afraid of. Scientists answered with plain words. Independent safety panels studied the risks in detail. They found a simple fact that calmed most experts. Cosmic rays slam into the planet all the time at energies equal to or higher than anything the accelerator makes. The universe has been running these experiments for billions of years without turning anything into a world eater. The math also shows that if a microscopic black hole formed, it would evaporate almost instantly and pose no threat. That technical comfort did not erase the image. The idea of creating a black hole touches a deep human fear. It feels like playing God with the fabric of reality. It also taught a lesson that mattered as much as the safety reports. When complex science touches public life, secrecy and jargon make fear grow. Clear explanations and visible safeguards became part of the price of doing big experiments. Even now, the rumor threads do not die. Some say the real danger was not the physics, but human error. They picture a switch flipped at the wrong time and a calculation missed. Whether those whispers are true or not, the moment changed how the world watches science. The safety reviews also changed how big science talks to the world. Independent panels looked at every scenario and put their findings on paper. The reports explained that cosmic rays already crash into the planet at higher energies than the collider creates. Those natural collisions happen all the time across the universe, and nothing catastrophic followed. Scientists use that fact to show the collider sits inside a safe cosmic environment. Some theories still made the headlines. A few physicists suggested that if space had hidden extra dimensions, tiny black holes might form more easily. That idea sounds dramatic. It also rests on assumptions that experiments have not shown. The collider looked for signs and found none. Physicists also studied how a tiny black hole would behave. The math says it would lose energy quickly and vanish. That is the simple version trusted by most experts. Beyond equations, the episode forced a cultural change. Laboratories started writing safety plans that the public could read. They held open days and made technical explanations simpler. They leaned into transparency because secrecy feeds fear faster than any error ever could. The machine itself went from scary headline to working instrument that helps us understand matter. It also left a different scar. People learned that even well-meaning research can spark existential talk in a heartbeat. That moment reminds us of an uncomfortable truth. Science is powerful, and power without clear oversight will always make some people imagine the worst. Trinity Test. Picture the New Mexico desert before dawn. Scientists huddled behind bunkers 20 miles from a tower, holding the first atomic bomb ever built. Some of them genuinely wondered if lighting that fuse would set the sky on fire. The fear was not fantasy. Physicist Edward Teller raised a terrifying possibility during the Manhattan Project. What if the extreme heat from a nuclear explosion triggered fusion reactions in the atmosphere itself, nitrogen in the air, hydrogen in water vapor? If those elements started fusing, the fireball would not stop. It would spread across the planet and burn away everything. Robert Oppenheimer, the man in charge of the science, took the concern seriously. He consulted Nobel Prize winner Arthur Compton. The question reached the top physicists of the era. Hans Bethe ran the numbers. A formal report followed. The conclusion was that radiation would bleed energy faster than any fusion chain could grow. The required temperatures would need to reach around 100 billion degrees. No fission bomb could get close. Still, the atmosphere ignition scenario haunted the countdown. Enrico Fermi offered to take bets on whether the bomb would merely destroy New Mexico or ignite the sky. That was dark humor, but it hinted at genuine unease. On July 16, 1945, the bomb detonated with a yield of about 21,000 tons of TNT. The fireball rose, the shockwave rolled. The atmosphere did not ignite. The math had been right. But the willingness to proceed, with even a tiny calculated chance of ending the world, still sits uncomfortably in history. That test changed everything that followed. It proved nuclear weapons worked. It opened the door to Hiroshima, Nagasaki, the Cold War, and every nuclear standoff since. The scientists who built the bomb later spoke of regret and responsibility. Some dedicated their lives to preventing the next use. Others carried silence. What lingers is the calculation itself. A group of humans knowingly ran an experiment that they had to prove would not end the world. They did the math. They trusted the math. They pressed the button anyway. That pattern would repeat in labs and test sites for decades. It still repeats today when new experiments push into unknown physics. The lesson from Trinity is not that scientists were reckless. The lesson is that progress sometimes walks right up to the edge of oblivion and asks if the numbers are good enough. Demon core. A small, polished sphere of plutonium sat under harsh lights, while tired scientists ran one risky test after another. They called what they did tickling the dragon's tail. The goal was simple enough on paper. Measure how close a mass of fissile material could come to going critical. The room smelled of metal and coffee, and the weight of tired judgment. The first accident came in 1945. A physicist dropped a tungsten brick too close, and the instrument flashed blue with radiation. He received a fatal dose and died weeks later. The second accident came during a screwdriver trick less than a year later. A man guided a reflective piece over the core with a screwdriver when the metal slipped. The core went supercritical, and the flash filled the room. He lived for a few days, but the radiation had already done its work. What exactly happens in a supercritical event? Neutrons bounce around and split atoms. Each split releases more neutrons that split more atoms. The reaction feeds itself and grows fast. In a weapon, that is the point. In a lab, it is a disaster. The incidents did not end the world. They nearly ended the careers and lives of the people in the room. They nearly erased the safety assumptions of post-war physics. Those accidents changed everything. Laboratories redesigned experiments. They invented remote handling. They stopped trusting pinch techniques that depended on steady hands and luck. Some veterans say the core earned its name because the physics inside looked like something alive and angry. Others argue that human hubris deserves equal blame. The story forces a hard question. How far should curiosity reach when a single slip can kill you and scar a whole field of research? The fallout forced labs to stop doing dangerous hands-on tricks. Engineers built tools so no one had to lean over a glowing metal ball. They moved experiments behind thick shields and long mechanical arms. Remote handling became standard. Procedures that once trusted steady hands were replaced by clear rules and checklists. Training also changed. New scientists learned to treat fissile material like a living hazard. They practiced drills until reactions became muscle memory. Emergency plans were drawn and rehearsed. Hospitals were told how to treat acute radiation injury. The language of the field turned strict and careful. The accidents also reshaped public trust. People learned that secretive work with weapons-grade material carries consequences beyond the lab. That mistrust pushed for oversight and for sharing what could be shared without endangering security. The story sits at the uneasy meeting of national defense and human safety. It asks whether some knowledge is worth the risk. There is a final, quieter lesson from those flashes of blue light. Science advances because people push its limits, but limits that kill individuals do not help anyone in the long run. The culture that grew after those events values safety as a kind of hard-earned wisdom. Researchers now accept that curiosity must walk hand in hand with caution. The room where those accidents happened is gone. The instruments have been retired. The names are recorded in books and training courses. The physics community did not stop learning. It changed how it learns. The cost of that change was human and permanent. Relativistic Heavy Ion Collider. Before the big machine in Switzerland grabbed headlines, another accelerator already faced the same accusations. It sat on Long Island in New York and smashed gold atoms together at nearly the speed of light. The goal was to recreate conditions from the first moments after the Big Bang. Scientists wanted to see what matter looked like when it was too hot to form protons or neutrons. Critics had a different picture in mind. What if smashing atoms that hard created something that could eat the Earth? The fears sounded familiar. Tiny black holes that might grow instead of evaporate. Strange matter, called strangelets, that could convert everything they touched into more strange matter. A runaway reaction that would turn the planet into something unrecognizable. Newspapers ran alarming headlines. A lawsuit tried to stop the machine. Public fear reached levels that surprised the scientists running the project. Brookhaven National Laboratory formed a safety committee. Distinguished physicists examined every doomsday scenario one by one. Their conclusion was clear. The collision energies were impressive for a lab, but trivial compared to cosmic rays that hit Earth every day. Nature has been running this experiment on the planet and the moon and dense stars for billions of years. Nothing catastrophic ever followed. The committee also pointed out scale. Smashing 2 gold nuclei together releases energy comparable to a mosquito bumping into a screen. That is not enough to create a dangerous black hole. Any theoretical micro-black hole would evaporate almost instantly through a process called Hawking radiation. Strangelets faced similar problems. They would only be stable at very low temperatures. The environment inside a particle collision is unimaginably hot. Hot, strange matter falls apart long before it could start a chain reaction. The collider turned on. It ran for years. It discovered a new state of matter called quark-gluon plasma. It taught us about the early universe. It did not create a single strangelet. It did not create a black hole. It did not delete anything except old assumptions about how matter behaves under extreme heat. The controversy left a useful legacy. Safety reviews became standard practice for any new high-energy project. The template developed for this machine was later used for the even larger collider in Europe. The pattern is now clear. Every time physics pushes into new territory, someone worries it might crack reality open. And every time, careful review finds that the universe already tested those energies long ago and survived. Zar Bomba. The largest explosion ever created by human hands happened over an Arctic island in 1961. The Soviets built a bomb so big that even they were afraid of what it might do. The original design called for a yield of 100 megatons. That would have released more destructive energy than all the explosives used in every war in human history combined. Scientists realized that a blast that size would create catastrophic fallout. Radioactive debris would spread across the globe. It could poison agriculture and water supplies for years. The weapon might kill more people from fallout than from the explosion itself. So they scaled it back. They swapped out some of the fuel to limit the yield to 50 megatons. Even reduced, it was still the most powerful weapon ever detonated. Still more than 1,500 times stronger than the bombs dropped on Hiroshima and Nagasaki together. The bomber crew had a 50% chance of survival, even with extensive modifications to their aircraft. They painted the plane white to reflect heat. They attached a giant parachute to the bomb to slow its fall and give themselves time to escape. When the bomb detonated, the fireball stretched 5 miles wide. It nearly reached the altitude of the aircraft that dropped it. The mushroom cloud climbed higher than the stratosphere. It spread more than 50 miles across at the top. The shock wave knocked the plane down by more than 3,000 feet before the pilot regained control. People saw the flash from over 600 miles away. Windows broke in Norway and Finland. The seismic pulse circled the Earth 3 times. At full power, this weapon could have salted the planet with fallout equal to a quarter of all the nuclear debris released since testing began. The designers knew this. They made a deliberate choice to hold back. That choice is what makes this story about more than raw power. The scientists understood they were building something that could scar the entire world. They decided there was a line even they would not cross. The test contributed directly to the treaty that banned atmospheric nuclear explosions 2 years later. The world saw what was possible and decided to step back. Castle Bravo. Scientists expected the bomb to yield about 6 megatons. The explosion that actually happened was nearly 3 times larger. That miscalculation turned a weapons test into an international disaster. The test took place at Bikini Atoll in the Marshall Islands in 1954. It was supposed to prove a new design for a practical hydrogen bomb. What it proved instead was that even the best minds in nuclear physics could be dangerously wrong. The problem was lithium-7. Physicists assumed this form of lithium would stay inert during the explosion. Instead, it reacted with neutrons and added fuel to the fireball. The yield jumped to 15 megatons. The explosion was the largest the United States ever detonated. It vaporized parts of the atoll and sent a cloud of radioactive coral and debris spreading across thousands of square miles. Fallout drifted over inhabited islands, where people had not been evacuated. Residents watched white ash fall like snow. Some children played in it. The delayed evacuation left entire communities exposed to dangerous radiation for days. 80 miles away, a Japanese fishing boat sat outside the designated hazard zone. The crew of the Lucky Dragon thought they were safe. They were wrong. Radioactive ash covered the boat and the men on deck. All 23 crew members developed radiation sickness. Their skin darkened. Their hair fell out. Nausea and pain followed. 6 months later, the ship's radio operator died from the exposure. He became the first confirmed casualty of a hydrogen bomb. The incident sparked outrage in Japan and around the world. It energized the anti-nuclear movement and forced nations to confront the human cost of testing. What stings about Castle Bravo is the gap between confidence and reality. The scientists believed they understood the physics. They ran calculations. They set a danger zone they thought was safe. Every one of those assumptions failed. The explosion was bigger. The fallout traveled farther. The victims included people who were never supposed to be at risk. The aftermath pushed for better prediction and tighter safety margins. It also planted a seed of doubt. If experts could be this wrong about a weapon, what else might they miscalculate? Starfish Prime. In 1962, the United States set off a nuclear bomb in space. The goal was to study what happens when you detonate a warhead at high altitude. What happened next surprised everyone. The bomb exploded 400 kilometers above the Pacific Ocean, with a yield of about 1.4 megatons. The flash was visible from Hawaii, nearly 900 miles away. Immediately, the electromagnetic pulse raced outward. 300 streetlights in Hawaii failed. Burglar alarms went off. Telephone systems glitched. The effect was far larger than anyone predicted. That was just the beginning. The explosion pumped charged particles into the Earth's magnetic field. It created artificial radiation belts that lingered for years. It supercharged the natural Van Allen belts that wrap around the planet. At the time, about 25 satellites orbited Earth. The new radiation damaged or destroyed roughly a third of them. Britain's first satellite had its solar cells wrecked. The Telstar communications satellite, launched just 1 day later, suffered crippling radiation damage to its electronics. The military learned that a single high-altitude nuclear explosion could blind a nation's eyes in space. Satellites that were supposed to last years failed in months. The radiation belts also made certain orbits dangerous for any new spacecraft. Astronauts and equipment would face higher exposure for years to come. What makes this experiment chilling is the unintended scope. The scientists wanted to understand one set of effects. They accidentally demonstrated that nuclear war could cripple infrastructure far beyond the blast zone. A weapon detonated in space would not need to hit a city to cause chaos. It could knock out communications and navigation and surveillance in a single flash. The test contributed to the partial test ban treaty the following year. Nations agreed to stop testing nuclear weapons in space, underwater, and in the atmosphere. The orbits needed to heal. The lesson needed to sink in. Today, the vulnerability remains. A single warhead at the right altitude could still fry satellites and darken electronics across a continent. Starfish Prime showed what was possible. We have spent 6 decades hoping no one tries again. Dead hand. Somewhere in Russia, a system waits. Its job is to guarantee that even if every leader is killed and every command post is destroyed, nuclear missiles will still launch in retaliation. They call it perimeter. The West calls it dead hand. It is one of the most unsettling machines ever built. The logic is brutally simple. Deterrence works only if your enemy believes you can strike back even after a devastating first attack. If an enemy thinks they can destroy your ability to respond, they might be tempted to try. Dead hand removes that temptation. It promises that retaliation will happen automatically, even if no humans are left to give the order. The system uses a network of sensors. Seismic detectors listen for nuclear explosions. Radiation sensors watch for spikes. Pressure monitors track shock waves in the atmosphere. If the system detects what looks like a nuclear attack on Russian soil, it checks for communication with the chain of command. If the links are dead and no one answers, it assumes the worst. At that point, special rockets launch. They fly across the country, broadcasting coded orders. Those signals trigger intercontinental ballistic missiles in silos and on mobile platforms. The retaliation begins without any human pressing a button. Some early designs proposed a fully automatic system that would remove humans from the decision entirely. The version that was built still requires activation by officials during a crisis. Once activated, though, the machine can act on its own. The system has been operational since the mid-1980s. It reportedly still works today. Russian officials occasionally remind the world that it exists. The concept comes straight from Cold War game theory. Mutual assured destruction depends on certainty. Both sides must believe the other will respond. Dead hand makes that belief bulletproof. But certainty comes with risk. Sensors can fail. Glitches can mimic attacks. A misread signal during high tension could start a launch sequence that no one intended. That is the terrifying trade at the heart of nuclear strategy. You build a system designed to end civilization as a backup plan, and then you hope the backup is never triggered. What makes Dead Hand disturbing is not its existence. It is the calm logic that created it. Smart people looked at the problem of nuclear deterrence and decided the only reliable solution was a machine that could destroy the world without asking permission. 1983. Incident. On the night of September 26, 1983, a Soviet officer sat alone at a monitoring station outside Moscow. Alarms started screaming. The computer screen showed one American missile heading toward the Soviet Union. Then it showed 4 more. The system confidence level was high. All indicators pointed to an incoming nuclear strike. Soviet protocol was clear. Report the attack immediately. Pass the alert up the chain of command. Let the generals decide whether to launch retaliation. Lieutenant Colonel Stanislav Petrov had minutes to act. If American missiles were really in the air, delay could be fatal. If the warning was false, reporting it could trigger a response that ended civilization. He made a decision. He did not report the launch. He told his commanders the system was malfunctioning. The next several minutes must have been unbearable. If he was wrong, nuclear warheads would start landing, and he would have betrayed his country by failing to warn them. He was not wrong. No missiles were coming. The system had been fooled by sunlight reflecting off high-altitude clouds at a rare angle. The satellite sensors saw a pattern that looked like rocket exhaust and interpreted it as a launch. Petrov reasoned that an American first strike would not begin with only 5 missiles. A real attack would involve hundreds. He also knew the early warning system was new and had problems. Ground radar showed nothing approaching. His judgment saved the world. If he had followed procedure, the alert would have reached leaders already on edge. A Soviet response could have launched within minutes. Retaliation would have followed. Instead, nothing happened. Petrov was quietly reprimanded for failing to file proper paperwork. The incident was classified and buried. It only became public after the Soviet Union collapsed. By then, the world learned how close it came to ending because of a software glitch and a cloud. Petrov never called himself a hero. He said he was just doing his job. But his willingness to trust his gut over the machine sitting in front of him may be the single most important decision a human being ever made. RHIC. The first true hydrogen bomb erased an island from the map. In November 1952, scientists detonated a device at Enewetak Atoll in the Pacific that proved thermonuclear weapons were possible. The word device matters. It was not yet a bomb anyone could drop from a plane. It weighed over 80 tons and required industrial equipment to operate. Still, it worked. The yield was 10.4 megatons. That is roughly 700 times the power of the bomb that flattened Hiroshima. The island where it sat simply vanished. The explosion vaporized the landmass completely. When the smoke cleared, there was nothing left but a crater a mile wide and 160 feet deep. The fireball stretched nearly 2 miles in radius. The mushroom cloud rose over 25 miles high. At its widest point, it spread more than 100 miles across. Radioactive debris fell on ships positioned 35 miles away. Waves 20 feet high scoured nearby islands clean of vegetation. Pilots who flew into the cloud afterward to collect samples faced heat, radiation, and electromagnetic storms that knocked out instruments. The test validated a new design for thermonuclear weapons. It proved that hydrogen fusion could amplify fission enormously. It meant that weapons could now reach yields measured in tens or hundreds of megatons. That realization changed everything about nuclear strategy. A single bomb could now destroy an entire city and poison the land for generations. The arms race accelerated. What haunts the story of RHIC is not just the destruction, it is the acceptance. Scientists and military planners knew what they were building. They watched an island disappear and called it a success. The people of the Marshall Islands bore the cost. Communities were displaced. Land was contaminated. Health effects echoed for decades. The paradise became a proving ground. From RHIC onward, the world lived with the knowledge that a single device could end a nation. That fact shaped diplomacy, drove treaties, and fueled fear for the rest of the century. We still live in the shadow of that fireball. The weapons are smaller now, but more numerous. The knowledge cannot be unlearned. The test that deleted an island also deleted any illusion that human technology had limits. RHIC and the strangelets. Before the Large Hadron Collider existed, there was another machine that faced the same fears. The Relativistic Heavy Ion Collider at Brookhaven smashed heavy ions together starting in the year 2000. Theorists warned that the collisions might produce exotic matter called strangelets. If strangelets were stable and carried a negative charge, they could theoretically convert ordinary matter into strange matter on contact. Touch anything and it would become like them. The reaction could spread until the entire planet transformed. Other worries followed. Microscopic black holes, vacuum collapse. The doomsday scenarios multiplied every time the machine was scheduled to turn on. Brookhaven assembled panels of experts. They analyzed each scenario. Their findings matched what later panels would say about the European Collider. Cosmic rays have been bombarding the Earth, the Moon, and neutron stars with energies far higher than any collider produces. If these scenarios were possible, the universe would have ended long ago. Strangelets only stay stable at extremely low temperatures. The heart of a collision is unimaginably hot. Any strange matter formed would fall apart instantly. Microscopic black holes require conditions that do not exist at these energy scales. Even if one formed, it would evaporate before it could absorb anything. The collider ran safely for years. It discovered the quark-gluon plasma. It taught us about the first moments of the universe. It did not create a strangelet. It did not delete anything. The controversy left a template. Any new physics experiment now faces safety review. That is a legacy worth keeping. Conclusion. The experiments in this story push at the limits of what humans can do. Some pushed too far and learned painful lessons. Others pushed right up to the edge and stepped back just in time. The pattern repeats. Curiosity drives science forward. Fear asks whether we should stop. Safety panels examine the math. Decisions get made. Not every experiment ends well. Mistakes kill people. Miscalculations expose whole communities. Machines designed to deter war almost trigger it by accident. What these stories share is the recognition that knowledge is not free. Reaching into the unknown comes with costs that may not show up until the damage is done. The answer is not to stop asking questions. Science has given us medicine, communication, clean energy, and understanding of the cosmos. Those gains matter. The answer is oversight, transparency, the discipline to slow down when the numbers look uncertain, and the humility to admit that even experts can be wrong. Every experiment that touched the edge of catastrophe left a lesson. Better safety protocols, new treaties, watchdog agencies, and review boards. Those are the gifts paid for in errors and near misses. They are the reason we are still here to tell these stories. The question is whether we will keep paying attention. The next forbidden experiment is probably being planned right now. Maybe it sits in a physics lab. Maybe it waits in a military installation. Maybe it lives in lines of code. Whatever it is and wherever it hides, the same rule applies. Push toward knowledge, but push carefully. Because some doors, once opened, cannot be closed.